It's working, right?
You can see your screen, yes.
Okay.
Please cut your mic. Well, I will do it for you actually.
Ouais, attends.
Non, c'est bon là.
Je suis bon là? C'est un peu chelou, mais ok.
Et on lève sur YouTube.
Okay. So hi again, everyone. I'm still Fabien, and not changed yet. And today I'm going to introduce you quickly how the atmosphere reacts to mesoscale variability of the ocean, and actually how this feature can affect locally the atmosphere, but also remotely and at other scales. So just to quickly introduce, we know that many coupling coexist over a large spectrum of temporal and spatial scales. And both one-way and two-way interaction are very important for both fluids. The main processes like control, actually, those processes, RC interaction control local heat and momentum fluxes, which is very, very important for both fluid dynamics. I'm going to focus on how the atmosphere reacts to the ocean, and I'm also going to talk a bit about upscaling effect. So what is the effect to take into account in the ocean in atmospheric modeling? So upscaling, when I say upscaling, it's for example like a seasonal variability. So it's not exactly the scale where the process happened, but it's more as an effect on larger scale. I'm starting here with a schematic, and this schematic represents actually the main processes that happen at the interface. On the left side of that schematic, we can see Langmuir circulation in the ocean. We have like marble rolls in the atmosphere, which is the equivalent. This is very important for clouds and fluxes. We have interaction between wave and current, wave and atmosphere. So that part is going to be more detailed by Swen tomorrow. And on the right of the figure, we have both thermal and dynamical current feedback. Okay, so current feedback is what is the effect to take into account that the ocean moves in computing the stress at the interface of the two fluids. And thermal feedback is how an ocean front, so if you pass from cold to warm or warm to cold, affects actually the stability of the boundary layer and some processes that happen there. All those processes are very, very important, mainly for heat fluxes. So this is very important to do like a heat budget, for example, of the Earth system. And this sketch represents the main processes that happen in a normal condition. And those heat fluxes can change, obviously, drastically, during tropical cyclones, for example. And we know that these heat fluxes can change by 1 order of magnitude. So this is important. All those interactions are very, very important for heat fluxes. I'm going to mainly focus on, so I'm going to introduce you first the main processes, so the dynamical processes, how the atmosphere dynamically balances to the ocean mesoscales. I'm going to mostly focus on thermal feedback and current feedbacks. I'm going to detail actually thermal feedback. There is two main processes, the downward momentum mixing and the pressure adjustment mechanism. We're going to see the effect of this when we integrate the model and how the atmosphere reacts to that. And we're going to see some effect and response in cloud and rain. So let's start. So thermal feedback, here what I show you is actually the correlation between wind speed and SST. On the top figure, we see like a very, very strong negative significant negative correlation. What does that mean? That means when the wind is blowing, the ocean tends to cool. Why? It's because the wind is blowing, that creates some mixing, and you have some so a deeper mixed layer in the ocean, so that tends to reduce the sea surface temperature. Okay, so more wind, the greater the wind, the cooler the SST. If we now pass a high pass filter to both fields, wind field and SST, and we do exactly the same computation, we see that a positive correlation emerges. So that means that at mesoscales, the greater the wind, the greater the SST, or the greater the SST, the greater the wind, because it's actually a positive correlation between wind and SST means that the ocean drives the atmosphere. So let's see what are the two main thermal feedbacks and processes that create this positive, this positive correlation. We have the downward momentum mixing, which is sketched actually on the left part of the slide, which involves large eddy within the bubble. So that concerns like the whole mixed layer column of the upper atmosphere, that acting on turbulent fluctuation of momentum from the top to the bottom. So when I say bottom, it is the interface actually with the sea. And here, as it's sketched, actually, we see actually a variation of SST with a warm eddy, right? And the atmosphere going to react to gradient of SST. Okay. So here, for example, if we pass from warm to cold, so from the center of the eddy to the left side, the wind tends to reduce at the surface. What does that mean? That means that we have a convergence sail in the atmosphere, and then a bit some upward movement that can create, as it's sketched there, also higher planetary boundary layer, and also some clouds, because we are reaching cooler temperature, and the clouds can form. Actually. The second mechanism is the pressure adjustment. Is actually a secondary circulation, which is forced by the divergence of the air temperature gradient, which is itself driven by the sea surface temperature. So here what we have a warm eddy, and we have actually on the top of the eddy, the warm eddy tends to warm up a bit the atmosphere there. That's creating some buoyancy in the air. So we have actually upward motion at the top of the warm eddy, or downward at the top of the cool eddy, right? So here we have upward or downward motion on the local maxima of SST, which means that we have a relation between wind divergence and Laplacian of SST. Now, a quick introduction on current feedback. So we're going to talk a bit more detail. Lionel is going to give some more detail about the current feedback, but here I present you the general idea. The general idea is like the transfer of momentum between the atmosphere and the ocean is given by the relative speed between atmosphere and ocean. So we usually compute that stress with a drag coefficient, CD, and we're going to multiply that by the relative wind between the two fluids. And if we write that the relative wind is actually air minus ocean, we're going to arrive at those equations that I'm not going to detail specifically, but we know that the stress and the current are like negatively correlated. What does that mean? That means that the ocean lose some energy, and this is what is called eddy killing. So here the map represents actually the sink of energy from the ocean to the atmosphere. And here there is another sketch done by Lionel, and actually I'm going to go pass quickly because Pierrick presented last week. But the idea is that when an homogeneous wind blows up over an eddy, if we take into account the two opposite currents, we're going to have like a more negative wind work on the negative wind work side and a bit less positive wind work on the positive side. So we lose energy. If we let the wind, obviously, because we are reducing the stress, so the wind is ready to blow a bit faster. So we have a partial re-energization of the wind done by ocean mesostates. Okay, let's dig into the thermal feedback processes. So I'm going to first start with the thermal feedback and the downward momentum mixing. As I said earlier, the front is going to actually alter the stability of the air column. So on the warm side of the front, the air column is going to be more unstable. So we're going to increase mixing from the top of the bubble to the surface. And on the cold side, we have actually a more stable boundary layer and even the creation of the internal boundary layer. So at the surface, we have the wind tends to blow faster over the warm side and smaller over the cold side. This process has been observed, and here I show you radio sound observation in the Eastern Pacific. And we can see that the boat actually crossed like a very, very cold eddy. So we drop the temperature about 3 degrees there. And we see that over the cold eddy, we have like a very sheared planetary boundary layer and also thinner actually. Over the warm side, so which is encircled on the red, we have actually a very homogeneous marble, and the thickness is extended. Here, as it's sketched on the left, we see that actually there is this relation which is nearly linear between wind divergence and SST gradients. So everything is happening over SST gradients. So to determine this linear coefficient, which called like a coupling coefficient, we use to plot wind scatter plot like this. So on the x-axis here, it's the gradient of SST. And for each gradient of SST, we're going to plot in y the wind divergence. And we see that the linear relationship emerge, and this is the coupling coefficient. Here in red, so that processes and that the coupling coefficient has been shown since 2 decades with satellite observation and over like a monthly field, like averages. And this is what I show in black. And in red, actually the daily responses. So we see that the downward momentum mixing is actually rapid processes, because we're going to see that at daily timescales and even like a smaller. So this graph has been done over the global ocean. Well, first, I want to just do a quick remark is the doubt of the linearity at the edge of the plot. And we see that actually the linear relationship is longer over the cold side, and this is hypothesized by the creation of the internal boundary layer. The creation of the internal boundary layer over the cold side, which is going to couple even more the SST structure to the wind divergence.
So what's the change in R?
Sorry?
What is the change in R you denominate?
This is the okay. Practically in x-axis is like SST gradient, And actually, the R denotes like it's along the background wind speed, and the anomaly function of the background wind speed. But that doesn't change the thing. You can also plot the SST, the gradient of SST. This is the same. So that plot has been like effectively on the global ocean, and the first question that we can ask to ourselves is there any environmental condition that can favor or this coupling, and actually the effect on this coupling coefficient with the background of our atmosphere. And this is what I show here on the next slide. On the right, this is exactly the same exercise. So the red dots is actually the same over global ocean. And here I differentiate with different background wind speed. And what we see that the violet curve has like a greater coupling coefficient. So that means that the greater the wind, the greater is that coupling coefficient. And on the right, same exercise again, but here I discriminate my ocean point with the difference between air temperature and ocean temperature. And what we see that the greater coupling coefficient is found for near neutral stability condition, which is a difference close to zero between air and ocean as a temperature. We can actually generalize that plot, okay? How we can do that? We're going to assume that this is a linear relationship and our hypothesis is right. So we can just calculate this alpha, which is the slope of that thing, in function of two main environmental conditions, which is the background wind speed and the difference between the temperature of air and ocean. And here I show you this generalization, which is here in color, the darker, the more important the coupling coefficient. Okay. And what we see, if there is a cross, that means that is not statistically significant. So we cannot hypothesize a linear relationship. But here, what we can see that the downward momentum mixing is actually effective for near neutral stability from moderate to strong winds. So now we can ask where those conditions happen and where we have most of the time this condition that favors this downward momentum mixing. And here I show you actually the map of the frequency where those condition is happening. So the condition with a black dot. And we see that those conditions happen mostly in moderate to high altitudes, and also for the eastern cold tongue. It's very important also for upwelling systems. So we see a big signal in Benguela, for example, or Canary, which is not surprising because we know that with the cold water from the upwelling, we get close to neutral stability of the atmosphere. Okay, so far we have talked about surface wind. Let's take a look. And here I propose you to do the same exercise that we done at the beginning, which is the correlation. Positive correlation means that the SST acts on the atmosphere. And I did that over the Mediterranean at different heights in the bubble. And what we see that we have significant correlation up to 925 hectopascal, which is in that area actually more or less in average the height of the bubble. So we have positive correlation between SST and wind until all over the bubble height. which is actually at daily time scales. Yes, sorry. So all the exercise is done at daily time scale. And this is in agreement with the theory, because as I said, when we are on a warm front, we know that we destabilize the air column. So it's all the large eddy that's going to create turbulence in the whole marble. Because all the marble is affected, we can take a look at cloud and rain response. And here I show you over the Mediterranean. See, again, same area. I show you in x-axis is actually the downwind SST gradient percentile. So that means that from 0 to 5, this is like the 5% extreme of the SST gradient of the negative of the warm to cold scenario. And on the contrary, 95 and above is a 5% extreme of a cold to warm scenario. On the left, we see the relative change in cloud cover, and on the right, we see actually the rainfall response. And what we see that when we have a scenario blowing from warm to cold, we create actually convergent cells that favors upward movement, and then we have more chance to have a cloud and more chance to have a rain. And at the contrary, if we are on a scenario cold to warm, we create divergence. So we do updraft movement, and we have less chance to have a cloud and less chance to have rain. So here it's a statistic because the cloud is forming in the atmosphere and then it's pushed by the thing. So it's really done like statistically by mean. We cannot track all the clouds and well. Okay, let's talk about the pressure adjustment now. So as I said earlier, and I introduced earlier, there is a secondary circulation driven by the sea level pressure anomalies, which are themselves forced by a local SST. Here I put you the sketch again. So this is this low pressure anomaly on the top of the maxima of the SST. And that's going to create upward movement and then creation of clouds and probably rainfall. These processes has been studied and shown here. I show you an example for a regional atmospheric model near the Hawaii Islands. And what we can see like we have a large, like warm eddy, and we have this upward movement and this secondary circulation that circulate like above this warm anomaly. And we see on the left temperature anomaly, so greater temperature, and so you increase the buoyancy, and you have this upward movement. And on the plot of the right, we see the cloud water content anomaly, and we see that just above the marble or within the marble height, we have creation of a cloud. This processes has been shown, well detectable on long time scales. And here I show you, for example, results from Minobe, 2008. And we see actually that we have very, very nice correspondence between sea level pressure Laplacian, SST Laplacian, and then wind convergence, and therefore rain over the Gulf Stream. Pressure adjustment is also acting on. Ariel did the same with the Agulhas, and you're right, I should actually update that things to show an example on the Agulhas current. Pressure adjustment is also acting on shorter timescales. And here on the left, I present you a graph from Lee and Carbone 2012. They found that the probability of a convective event is triggered by the SST patches in the tropical ocean. Okay, so we can see like here the red PDF, for example, and we have way more probability to have convective events over warmer SST. It has been shown also that this process is very important in a tropical area also after the passage of a tropical cyclone. Why? Because a tropical cyclone like pace, and we have like a very, very cold wake in the middle of the ocean, which is like a very, very large structure. And the secondary circulation like can develop actually because the cold wave is quite stable for at least a week. And here we see like the positive anomaly of sea level pressure and then the development of actually the secondary circulation. I propose you to do exactly the same exercise as we did for DMN, for the downward momentum mixing. And here I show you, I plot then the Laplacian of the SST in X, and in Y, I plot the wind divergent cells. And we see also a nice linear relationship is appearing, and also at daily time scales. And in black is actually the monthly time scales that we did exactly the same for downward momentum. So let's try to find the environmental conditions that can favor and this pressure adjustment and can favor this angle of the slope, right? Same. We are used to that plot now. So the color, the darker the color, the more important the coupling coefficient. And if there is a cross, that means that it's not significant. And what we see that two main regimes appears. So this is not as DM. So the more important coupling coefficients are found for very, very weak winds, near stable or slightly unstable, which are the black dots, and the yellow dots, the white dots, sorry. It's for like very, very unstable condition and very, very important wind. Let's plot the location of those events, and the top map show actually the slightly unstable low wind regime, which is not surprisingly around the tropics. Right? We can explain actually the processes by the advecting time scales. So the wind is very blowing steadily, not rapidly. So he has the air parcel has a time to fill the SST and to develop the secondary circulation. The white dots now are plots in the second map, bottom map. And what we see here, we see actually those events are happening over western boundary currents. So how we can explain those events is actually by extreme heat fluxes. So we are in a very, very unstable condition, probably with very, very cold air, especially this is especially the case for the Gulf Stream, for example, because the air is coming from the continent, is flipping cold because this is winter, and that air parcel will meet the Gulf Stream, which is very, very warm. So we have intensive, super intensive heat fluxes. Super intensive heat fluxes. That means that the ocean is able to reply very, very quickly.
How would it trip with the
Yeah, sure. Yeah, sure.
I see that so what does that mean? The blue shade.
Over the negative value.
Yeah.
Yes. That means that here for like a very, very unstable air column. Very unstable, so means like a very negative air sea temperature difference and strong winds. The atmosphere, well, the pressure adjustment is actually efficient. Okay, so our slope of the regression, this coping coefficient, is stronger. So the slope is more steep. And as I said, we extend that by very unstable and large wind means that the heat fluxes are like extreme.
Now we don't have it anymore by Zoom. I want to look at it on YouTube.
Okay,
So,
okay.
I have to share the whole screen maybe.
Je dois display setting. Je fais mirror, non?
Je me rends.
Sorry guys for that.
Non.
Okay. Okay, so now, so far, what we've seen the local response. Okay, as I told you, downward momentum mixing, we are going just what is happening over the gradient. Okay, and pressure adjustment is what is happening over the local maxima or local minima of the SST. Now, the next the next part is actually what important it is to take those processes into account when we do an atmospheric simulation. So to show that, let's go to the southern Africa, and the main question here is like, what is actually the effect of the full spectrum of SST in terms of rainfall over the continent and over the whole the basin. Okay. Here I sketch the main processes, what is happening in southern Africa, so south of the equator, in summer. What we know that the ocean is, that we have the agulhas, the retroflexion, a lot of eddy there. We have a very cool ocean here because it's upwelling. And here we have a semi-parent, like very, very important front called Angola-Benguela front. Well, Serge is very interested in that front actually. That separates the warm tropical ocean to the cool upwelling system. So this is for an ocean point of view, but this is like very, very simple. And in the atmosphere, actually, we have incoming flux, moisture flux from the ocean, from three parts, actually. And those fluxes actually converge here at the northern Namibian border with Angola, making this guy, which is called the Angola low pressure system. Okay? And this Angola low pressure system is forced and maintained by the moisture flux, incoming moisture flux, and is very important because it's going to redistribute the moisture throughout the full subcontinent, and it's very, very important for rainfall variability during summer. What is the effect of mesoscale SST on these atmospheric processes? So we're going to make an atmospheric simulation and make the atmosphere seen either the full spectrum of SST. So here I show you two snapshots. Here we have the smallest SST that we can with the grid, with the atmospheric grid. And here we have actually only the large scale thing. So we have no more eddy. We can even like distinguish like very, very badly the agulhas. And the Angola-Benguela front is actually very, very smooth out. And the front is over like hundreds of kilometers. And it's not like very, very thin like in that case, right? So we're going to integrate that model over like a season and see what is happening. So first on the left, I show you our control run, which is the run that see the full spectrum of SST. And we verify that we have the main structure. So this is the Angola low in black contours. We have incoming moisture flux, and purple dots like are representing more or less the cloud system. No? Let's see what is happening with the model that see only large-scale SST variability. And here I show you actually the Angola low. So black contour, our control run. Orange one, this is actually the one forced by only large-scale SST. And we see that actually the Angola low is deeper, with like the black line here, is deeper in the core of the summer if the atmosphere seen the full spectrum of SST. So if this pressure adjustment and downward momentum mixin is actually present like any time, so we're going to change near surface variability of the atmosphere, and that's going to change actually all the basin scales, large scale, regional scales dynamics, that resulting in a deeper Angola low. And obviously, this is very important for rainfall, and this is the main difference in terms of rain between the two simulations. And what we see that especially it's the Angola low region, it's raining like way less if the atmosphere doesn't see the mesoscale activity. Tell me, Serge.
Yeah, I was talking about the previous slide. Yes, that the difference is only happening from December to April, right?
Yes. So the Angola low is deeper in the core of the summer, and actually it's present like over 6 months practically, but in the core of the summer, this is a tropical low. Okay, so on the other season, this is more a heat low. So that means that the instabilities of the low pressure is mainly driven by temperature, and on the core of the summer, this is a tropical low. So the instabilities are coming from the moisture. Okay, so that's why it's actually important for the local rain and also for all the distribution of clouds all over the continent. And this is what I show here. And practically, what we see like even like we have like a remote signal in Botswana, Mozambique, which is way drier actually, with a lower, well, a less active Angola low. Here there is a big signal as well, but it's actually my hypothesis is like the ITCZ is responding to ocean mesoscale. But I could not reply to that question because my domain is a bit too small and too constrained. This is, I think, an ongoing work with other simulation, actually. Here, I'm going to pass like very, very quickly. But practically, what I did here, we are over the global ocean. We know that we have the two mechanisms. The red is the downward momentum mixing, the blue is a pressure adjustment, and I do a ratio of PDF for a moment that favors vertical velocities, updraft, and the moment that favors downdraft. Okay, I do the ratio over all the cloud cover range and over total precipitation, like millimeter a day. The only thing that we can retain from that figure is that value here. We see like for DMM, this is very important. We double the chance to have like a free sky, cloud-free sky if we are on the cold to warm scenario. Okay, I'm going to end up with another example of the effect of the current feedback now on the atmosphere. So to do that, with Lionel and another colleague from Barcelona, we have run like this experience, which is a fully coupled ECS3 model with an ocean globally. And in one of the two, we did that like a twin experiment. In one of the two, we cut the ocean current. So the atmosphere doesn't see the current to compute the stress. Okay. And we integrated actually this model like 25 years, and we have like both 25 years that we can see. What is the main effect of this current feedback on ocean dynamics is actually the subject of the talk of Lionel. I'm just going to show you this image, and practically the current feedback tends to act as an eddy killer. There is a transfer of energy, so it's a sink of energy for the ocean. So the ocean mesoscale is less active. That tends to stabilize the western boundary current. As a result, we have a large-scale SST gradient from, for example, if we focus here in North Atlantic, we tend to warm the Atlantic. So that means that the large-scale gradient of temperature is diminishing. As a consequence, the large-scale temperature in the atmosphere at 850 hectopascal also decrease. And as a consequence, we have less, you know, that storm track, which is very, very important for extreme rainfall. So this is all the storms that develop mostly high latitudes. We have like a couple of storms here in Cape Town during the winter. So this is like a front is happening. So we call that like a front storm track. So this is where actually fronts are developing over the ocean. And that creates actually a massive no, I think the advection is a leading process. So you advect more warm water.
It's because you change the path of the boundary currents, mainly, and then you shift the position of the gradients, the mean gradients.
So you have like warmer water, a bit further north. That tends to decrease the large scale SSC.
The carrier that changes.
Yes, exactly.
Instead of just
It also modifies the path.
Yeah.
Yeah, so like here we have the eddy growth rate, which is a nice variable that shows how fast a atmospheric front can grow, how far and this is like a nice thing to plot by, for example, the activity of the storm track. And here we see that as a consequence, we actually diminish storm track in the North Atlantic, for example, of about 15%. And over the Agulhas, this is actually shifted because the path of the Agulhas and the retroflexion is not at the same place. So here we see thermal feedback. You know that thermal feedback has a direct effect and very, very strong effect on the atmosphere. Here with the current feedback, the hypothesis is it's a second effect. So the current feedback affects ocean dynamics a lot. This is the talk of Lionel. And because the path of the main currents are like a bit changing and there is less eddy, with thermal feedback, there is a response in the atmosphere. So this is actually the combined effect of courant and thermal feedback. I'm going to finish here, and I'm going to just conclude. Well, my conclusion, I'm not going to read the conclusion, but we saw particularly the two main effects of thermal feedback, which are like very, very important for the atmosphere because that create convergent cells and divergent cells. So upward or downward movement in the atmosphere in the full bubble, and have direct effect on creation of clouds and rainfall. And this is very, very important for larger scale atmospheric dynamics, as we've seen for the Southern Africa, for example, and further for also storm track, which is we know very, very important to redistribute the heat in the Earth system. I'm going to stop here. Thank you.
Any questions? And then if you want, you have the whole week to ask other questions. If you don't have any now, but feel free.
Sure.
So in the case of an upwelling system, the winds are by definition parallel to the SST gradients. So is the effect maybe stronger, this kind of ocean current feedback locally? Does it maybe depend more on the onshore components of the winds? Or like maybe in an area, does it matter? Is the onshore component, in those parts we shown before with the DSST by DR,
Yes.
The gradient alongshore, the gradient with respect to the direction of the wind, right?
Yes.
In
So
an upwelling system, the wind is kind of along the SST gradient wouldn't be that high.
yeah, sure. So you have the downward momentum tends to reduce the wind on the cold part, so onshore.
Yeah.
And